Hi everyone, this is group number 88 and we have worked on computer vision assignment. So our project is about unsupervised cross-modal anomaly detection and which we have done using CT and MRI brain images. Our goal was to train model only on the normal looking brain scans and then detect abnormal cases based on how much they deviate from the normal pattern. And as suggested, what we did is we picked up a Kaggle dataset that contains those images, and it was like 4,900 images for each modality. If you look at here, yeah, correct. So even though the dataset claims that the CT and MRI images are paired, but many of them were incorrectly prepared. So the first thing that we have done is make them paired, find out the relationship between those two images, CT and MRI. And before doing any modeling, so we thought of fixing those issues first. So what we did is we extracted few of the file names, those IDs, etc. And then we started some sort of data cleaning process, which is again the initial stage of the doing any modeling on the on anything. Come down. So but after fixing those data set, the what we started is the small pre-processing step where we converted all the images into 128 by 128 and and into a grayscale images. So the high level of our project is more like that we first perform the pre-processing step, which includes cleaning, resizing, normalization, pairing, all that stuff. And the second part is what we did is we learned models during CNN-based autoencoder. That's one VA, variational autoencoders, and then we tried out the transformer-based architectures. Now, based on those, what we did is we picked up this thing. So based on those data sets, we trained these models and we computed the reconstruction and latent space to evaluate how well each model learn these normal patterns. And finally, we calculate the loss and stability during training, and we selected the best performing models, and then we moved to evaluation and the anomaly detection stage.
So the data sets were limited in size, so we had to apply some augmentation to it so that it is more generalized. We use random affine transformations like small rotations, translations, intensity scaling, and Gaussian. We added some Gaussian noise injection. And the issue was the CT and MRI images represent the same brain anatomy. So any transformation done on one thing had to be on the CT had to be done in the MRI too. So we implemented a pair geometric transform for this. In the process, we expanded the training data set by 3. This reduced overfitting and made training more stable, especially for the deeper models. So we tried for the models, we tried 3 things: a standard CNN autoencoder, a variational autoencoder, and a transformer. We used a shared latent space, basically averaging the features from both encoders. To be honest, the CNN autoencoders gave us the best result. The transformers were a bit too complex for this amount of data, so we stuck with the CNN.
In terms of testing this model, so we have, as Akhil was mentioning, we have implemented 3 models, and but testing this was tricky because remember that it's a unsupervised data, so we don't have labels telling that this is a tumor. So what we rely is on a reconstruction error. We basically ask the model to recreate the image, then so we subtract that result from the original. If the scan is healthy, you'll see that the images that appear, the map is nearly black, as you can see on the screen, and the difference is nearly zero. But if it's a tumor, the model doesn't know how to draw it. So it messes up that spot. When we look at the difference map, that particular area lights up. It gives us a really nice visual way to explain that why the model thinks that something is wrong there, and we are able to identify the anomaly.
As the recording was not completed. The most interesting part was definitely validation. At first, we added random noise to the image to simulate the anomalies. We got an AUC score of 1.0, literally perfect. We immediately knew that it was wrong. It was just too easy for the model to spot the noise. So we went back and wrote a custom function to inject small noises. As you can see now, the graphs are overlapping. The anomaly graph and the normal graphs are overlapping. That basically is saying the distribution is shared now. With this, the AUC has dropped to a realistic zero point 0.6, and this proves the detecting of actual anomalies is much harder problem. In real world, a tool like this could be a huge triage. Imagine a system that automatically flags a suspicious scan in a busy ER, so the radiologist looks at those first. Thanks for listening.
So to conclude, as you can see, we did a visual qualitative analysis by visually examining the reconstruction error maps for the samples identified as anomalous by the model. So the scans flagged as anomalous clearly show higher error concentrations, as you can see in this screen. These lead to often corresponding to irregular structures. However, in contrast, for the normal scans, if you scroll down, the reconstruction errors were generally low and evenly spread out across the image. So the model is able to identify the anomalies in the CT and the MRI scans. Thank you for joining.